Well, good evening, everybody. Thank you for coming to this astronomy talk, and hello to all the online audience. The format of this talk is that I'm going to show some of my astronomical pictures and explain something about what's in them, and then my friend and colleague, Dr. Christian Sass, is going to talk a bit about the technology that makes this all possible, and Vishy Anand is going to show some of his pictures and explain how it all works in practice. So, let's start.
Jonathan, can you speak to the hearing aids at the back here?
I'll adjust it. Just
Okay.
I'll adjust it a little louder.
Well, Douglas Adams' famous book restricted itself to the galaxy, but we're going to view lots of things not only in this galaxy but also outside the galaxy, so the scope of this talk is really going to be cosmical, shall we say. Well, if you look at the night sky outside this tournament hall, for example, you probably think, well, it's not very interesting. You can see the moon, a few planets and maybe 100 stars. But that's partly because of the light pollution in London, which blots out a lot of the detail of the night sky. If you go to somewhere that's really dark, the Milky Way is a truly spectacular sight. And if you have binoculars, then you can see a host of interesting objects in the sky. But of course, most of the interesting objects only really show their full glory when you use a telescope and you use long exposure photography. And all the images I'm going to show you this evening were taken with an exposure of about 1 hour. So the telescope has to track the object across the sky for 1 hour to compensate for the rotation of the Earth, and the shutter on the camera or imager is open for the whole time, collecting light. So you can achieve sensitivities that are far beyond that of the unaided human eye. Now, I'm going to start near to the Earth, relatively speaking, and gradually go further away. Now, astronomical distances are usually measured in light years, and in terrestrial terms, a light year is a truly vast distance. It's about 10 trillion kilometres. But on the astronomical scale, a light year really isn't very big at all. For example, our galaxy, the Milky Way, is about 100,000 light years across. Now, on the basis that it's much more interesting to show photographs of distant and exotic places rather than photographs of your backyard, I'm going to start already 450 light years from the Earth with the Pleiades, which is a naked eye object. You can even just about make it out in light polluted London, and it's an open cluster of stars, sometimes called the Seven Sisters because there are 7 naked eye stars visible from a dark site. But what you won't see if you look at it with the naked eye is this nebulosity surrounding the stars, which is what we call a reflection nebula. The light you see is reflected of grains of dust in interstellar space, and the light of these hot blue stars is reflected from the dust and reflected in our direction, so we see this kind of cloudy appearance around the stars. Now, sometimes these nebulae, these clouds of dust and gas in space, are signs of star formation. But in this case, it's a complete coincidence. The stars of the cluster just happen to be passing through this cloud of dust and gas, and we see the light reflected in our direction. Now, if we go on slightly further away, now this is a really interesting image because there are so many things in it. I mean, first of all, this is another reflection nebula. It has this characteristic bluish light. And the reason it looks bluish is not only because the light of the stars inside it is blue, but it's the same reason that the sky of Earth is blue. The dust grains reflect the blue light better than other wavelengths, so it looks blue. And up here to the upper left, we can see the giant star Antares. Down here, there's a cluster of stars. It's a globular cluster. And that's actually much further away. That's about 7,000 light years away. So it's much further away than most of the other things in this image. And just here, at the middle top or to the right, there's a dark nebula. You can see there's a dark streak here obscuring the light of the stars behind. And this happens when you have an opaque cloud of dust and gas blotting out the light of the stars which are more distant. on to the next image. And here we see a beautiful example of a reflection nebula, a star inside the nebula, a very bright blue star, and the swirls of dust and gas which surround the star are reflecting the light of that star in our direction. So you're already 1,000 light years away from Earth. All the other points of light here you can see are other stars within our own galaxy.
John, how wide is that dust cloud?
It's about, okay, I'll just go back to that. That dust cloud is about 3 light years across. So that's quite a long way. If you consider the distance from the Sun to the nearest other star, the Alpha Centauri system, is about 4 light years. This is 3 light years across. It's big. Now this is interesting. This is called the Dumbbell Nebula, and it's what's called a planetary nebula. Now that's an extremely misleading name because this has nothing to do with a planet. It's very large. It's about 2 light years across. And here you see part of the answer to one of the great mysteries of the cosmos, which is that immediately after the Big Bang, the universe consisted only of the very lightest elements, almost entirely hydrogen and helium, with just a tiny trace of lithium. So how did these elements like carbon and oxygen, which are essential for human life, come to be all around us? And you can see part of the answer here. What's happened in this image is that the central star of the nebula is an old dying star. And when a relatively small star, say of the size of the mass of the Sun or slightly larger, dies, its outer layers are thrown off into interstellar space. Now these elements like carbon and oxygen and nitrogen are formed by nuclear fusion within stars. The light elements, hydrogen and to some extent helium, are combined in fusion reactions to make carbon, nitrogen and oxygen. These are then expelled into space. And you can see here this greenish tinge is oxygen. The reddish streaks are nitrogen. So here you see elements vital for life being cast off into space to form the basis for the next generation of stars, which will be formed from clouds of dust and gas seeded with the debris of stars that have already died. The central star becomes a white dwarf, by the way, a white dwarf star, a very small star, perhaps about the size of the Earth, and with nuclear fusion reactions die out and the star eventually cools and disappears from view. Okay, this is one of the most famous objects in the night sky. It's a naked eye object in the constellation of Orion, and it's a region of very active star formation. Here's an absolutely massive cloud of dust and gas. Parts of it are collapsing. If you look at the very brightest region here, this has already collapsed to form a cluster of very bright stars, and other parts of the nebula are condensing to form stars in the same way. And it's the closest area of active star formation to the Earth. So this is absolutely fascinating for astronomers because they can see the process of star formation, star creation. Of course, it takes too long to say, I can't say it playing out before your eyes because the process takes a very long time. But you can see stars in different stages of formation within the Orion Nebula, and so work out how it is that these massive clouds collapse to form stars and planetary systems. And the next object is of particular interest to chess players. It's the Horsehead Nebula, which you can see here. And the Horsehead Nebula, and it's an astonishing coincidence, it looks so much like a chess knight. I just can't get over it that some aliens didn't just put it there like that. But anyhow, what it is one of these dark nebulae. It's an opaque cloud of dust and gas which happens coincidentally to light in front of a bright nebula. So you can see this pinkish glow, which is in fact characteristic of what's called an emission nebula, which is a nebula where the gas is glowing with its own light. Typically, hydrogen gives out this pinkish reddish glow, and it just happens that there's a dense little cloud of dust and gas in front of that, which blocks out the light from the emission nebula and creates this silhouette of a knight's head. In fact, there's another interesting nebula middle left. That's called the Flame Nebula because its appearance is like a flame. And there you can see light from the nebula, again blocked out by streaks of dark nebula lying in front, giving this strange appearance of a flame, or perhaps I sometimes think it looks a bit like a leaf. So now we go on to something completely different. This actually is only a part of the Veil Nebula. It's one of those things that if our eyes were more sensitive, the night sky would actually be a riot of interesting nebulae and colours and clouds, but unfortunately our eyes aren't sensitive enough to see this structure, which if it were visible would be something like 10 times the width of the full moon. It really occupies a significant part of the night sky, and this is actually only a small part of the Veil Nebula. Now, these wispy filaments look quite innocent, but actually they're the remnants of a real cosmic catastrophe. They're what's left over from a supernova, a star that exploded. And by tracking the movements of this cloud, we can work out that the star must have exploded between 5,000 and 8,000 years ago. And what you're seeing here is actually the shock wave, or part of the shock wave from this explosion. As it spreads out into interstellar space, it compresses the gas in front of it and creates these filaments of the shock wave. And it's, as I say, the whole thing is absolutely enormous. It's just a small part of the whole structure. You can only, unfortunately, see it with long exposure photography. Otherwise, it would be a really spectacular part of the night sky. Now we're getting slightly further away again. This is a massive emission nebula called the North American Nebula because it supposedly resembles the outline of the North American continent. Although in this image I think you have to turn it upside down in order to get the resemblance. I think this is supposed to be the Gulf of Mexico here. Now, this is another, you often think of telescopes as having great magnification and being able to magnify very tiny objects in the night sky. But in fact, many of the most interesting objects are quite large. And this view here is a wide field view. The left to right distance here is about 10 times the diameter of the full moon. So this nebula, which is in fact just too faint to see with the naked eye in a dark site, would again be a very prominent feature of the night sky if only our eyes were a bit more sensitive. And in fact, there's a bit of a mystery with regard to this nebula because the glow must be coming from a star whose radiation is exciting the gas to emit this pinkish light, but it's not known which star is actually responsible for the emission. There are several stars at roughly the right distance which could be responsible for the emission, but nobody knows for sure which one is responsible for causing the gas to glow. Now we're going twice as far away again, over 3,000 light years. This is the Cocoon Nebula. You see, it's a very, very nice colour, and it's partly an emission nebula and partly a reflection nebula. And also you can see off to the upper right and here there are traces of dark nebula. I really included this because I just like the look of this nebula. It looks very nice and it's got a very attractive colour. And also you can see in this picture the many different colours of stars. Some stars are bluish and some are reddish. Hotter stars are bluish, cooler stars are reddish. And although, because the human eye is not very colour sensitive at low light levels, most stars you see look sort of whitish when you look at them. But in fact, when you look at them through a telescope, they have distinct colours, which is very visible in this picture. 4,000 light years away now, this is an emission nebula, which is also a star-forming nebula. Parts of it in the centre have already collapsed to form stars, and here, a bit to the left of centre, you can see another cluster of stars which have been born from this massive cloud, which is 55 light years across in this direction and 20 light years across in this direction. So it's absolutely huge. This is an interesting nebula. this actually is one of the brightest stars in the constellation of Cygnus, and the nebula appears to surround this star, but actually the nebula is much further away than the star is, about 5,000 light years, and this one is even larger. It's 100 light years across. And you can see there are many dark lanes in it. There's this massive dark lane in the middle, and also smaller areas of darkness which are caused by clouds of dust and gas which are blocking the light from the more distant nebula. Okay, this is called the Rosette Nebula. It's again very attractive, and in a way it's similar to the earlier Lagoon Nebula, in that here we have an emission nebula which is also, parts of it are also collapsing to form stars. And you can already see this cluster of stars in the middle here have been formed. And in fact, one of the things that tends to happen when part of the nebula has collapsed to form stars is that the radiation pressure from the light pressure from these stars tends to blow a hole in the nebula. And you can see that in the middle of the nebula here, that part of the nebula has actually, the gas has been blown away by the light pressure from the stars which have already formed. Okay, the top part here has this characteristic pinkish reddish hydrogen glow of an emission nebula, and the bottom part is whitish or slightly bluish, and that's a reflection nebula. And you can also see again dark lanes here formed by opaque clouds which are in front of the main nebula. Now the next object is very interesting. It's the Crab Nebula. Now this is another supernova remnant, and if I just show you, highlight a bit, I hope you can see there are two stars close together in the centre of the nebula. Now the fainter one, the one that's to the lower right, is the star that exploded. Now this explosion was observed by Chinese astronomers in the year 1054, so we know exactly how old this nebula is or how long ago the explosion took place. I mean, of course, it took place 6,500 years earlier because it took that length of time for the light to reach us. But speaking in terms of what we observe, the explosion took place, or the light from the explosion reached us just under 1,000 years ago. And here is another part of this mystery of the cosmos, because I explained earlier how these smaller stars created elements like carbon and oxygen, which are important for life. But these smaller stars can't make the heavier elements, metals like iron, which are very important, not only because the core of our planet consists largely of iron, but iron is also an important element in biological processes. For example, every molecule of hemoglobin in your blood contains 4 atoms of iron, and this is where the oxygen actually binds to these atoms and is carried around your body to be released to support the tissues of your body. So where did the iron come from? And iron, it being one of the heavier elements, can only be made in the core of a massive star. And these massive stars, when they reach the end of their life, they explode in a supernova explosion, and what's left is either a neutron star, as in this case, or a black hole. And the iron and other heavy elements are scattered out into space and again form the basis for the next generation of star formation. So you can think that every atom of iron in the hemoglobin in your blood was once in the core of a massive star before being blown out into space in a supernova explosion. Now actually this neutron star is a pulsar. It rotates about 30 times a second, and obviously you can't see it on a long exposure photograph, but if you use a really large telescope, you can see that the light from this star is flashing on and off 30 times a second. As the star rotates, it sends a beam of light out in our direction like a lighthouse, and so we see this, you could see this star flashing. And the neutron star itself is only about 30 kilometers across. It's very small. And what's amazing is that we can see something only 30 kilometers across from a distance of 6,500 light years. But perhaps that's less amazing if I say that this neutron star is putting out 75,000 times as much energy as the sun, which explains why we can see it over such a vast distance. Okay, from a supernova that has occurred, the one that hasn't yet occurred. This is the Carina Nebula. It's 9,000 light years away. It's a massive star-forming region. And down in this very, very bright region down here, there is a star, Eta Carina, which is quite possibly the largest and most luminous star in the galaxy. It weighs about 100 times as much as the Sun, and it gives out 5 million times as much radiation as the Sun. Now, such large stars have very short lifetimes, and they're extremely unstable. And astronomers believe that this star will go supernova sometime in the near future. Now, near future to an astronomer can be quite a long time, and astronomers disagree. Some believe it's going to go supernova within the next decade. Some believe it might still last several hundred years before the catastrophe overtakes it. If it does explode in our lifetimes, it will certainly be a spectacular sight, because such a large star will explode not in a supernova, but what's called a hypernova, which is a supernova's big brother, as it were, and only the most massive stars can create these hypernovas. You don't need to worry. 9,000 light years is a really long way away, so it can't do us any damage, but it would be clearly visible in the daytime sky. It would be so bright. Now, on to the next. Okay, this illustrates something interesting. I mentioned earlier light pressure is very important. Now, when you hold your hand out to the sun, the sunlight falling on it does actually exert a small pressure on your hand. It's so small you can't feel it. But in space, where this light pressure can accumulate over thousands of years, and remember in space there's nothing to resist motion, so once something is set in motion, it will continue to move. This light pressure is actually one of the main forces which shape nebulae. And here you can see it particularly clearly. You can see this bubble here, which has been blown in the nebula by the light pressure from one of the bright stars inside it. So here's a vivid demonstration that light does actually exert pressure when it falls on a surface or on a gas molecule or anything else. And as I say, even though it's small by terrestrial standards, when it operates for thousands and thousands of years, it can have a major effect. Okay, now we're getting to the borders of our galaxy. I said before it's 100,000 light years across. That's if you measure it in the plane of the disk. But the disk of the galaxy is relatively thin. So if you look perpendicular to the plane of the galaxy, you don't have to go that far before you're actually out of the galaxy. Now, orbiting our galaxy are a number of what are called globular clusters. And this is the largest of these globular clusters. You can see it contains an enormous number of stars. It contains about 10 million stars, and they're really closely packed together. In our part of the galaxy, the average distance between the stars is measured in, say, 5 light years. But in the center of this Omega Centauri, stars are within 1/10 of a light year of each other. So if you're on a planet orbiting one of these stars, the night sky would be truly spectacular. It would be filled with brilliant, brilliant stars. Now, these globular clusters are balls of very old stars. They were formed early in the history of our galaxy, and they've been orbiting our galaxy ever since. Now, in fact, this particular one is probably a special case because it's much larger than any of the other globular clusters orbiting our galaxy. And a lot of astronomers suspect that, in fact, it's not a true globular cluster formed the same way as the other ones, but is actually the core of a dwarf galaxy which was caught by the gravity of the Milky Way and pulled into an orbit around the Milky Way. And the gravity of our own galaxy has pulled the outer regions of this dwarf galaxy apart, leaving only this dense cluster of stars, which was the core of the dwarf galaxy before it was subjected to the destructive tidal gravitational forces of the Milky Way. Okay, I'm going to go on to other galaxies, but first of all we're going to make a kind of pit stop in intergalactic space, because intergalactic space isn't actually completely empty. There's quite a lot of interesting stuff there, and this is the Large Magellanic Cloud. It's a naked eye object visible, alas, only from the southern hemisphere, and this is a kind of sub-galaxy of our galaxy. You see, it's outside our galaxy. It's 160,000 light years away. And if it weren't so close to the Milky Way, it would qualify as a galaxy in its own right. it's got about 1% of the mass of our galaxy. Now, the object I'm talking about here is this area here. You can see also many other stars, and these are stars, say, here and here. These are stars in our Milky Way that happen to lie in the same direction, but this huge condensation of stars in the middle, and including this area to the lower right, that is the Large Magellanic Cloud. As I say, about 10 billion solar masses, 1% of the Milky Way, and it's about 14,000 light years across. Now, I'd like to draw your attention to one little area here on the lower right. Now, that is a very interesting object in its own right. It's called the Tarantula Nebula, and now I'm going to show you a close-up image I took of that part of the Large Magellanic Cloud. This is the largest star-forming region in any of the nearby galaxies. It's 500 light years across. It's not quite clear why there's this massive region within what is actually a relatively small galaxy, but it could well be that the gravitational effect of the Milky Way has caused some of the large clouds of dust and gas in the Large Magellanic Cloud to collapse in perhaps a more dramatic fashion than they would have done otherwise. But here you can see lots of filaments of gas, and you can see lots of stars, clusters of stars forming within this gigantic star-forming region. So now we go on to the nearest sizable galaxy, the famous Andromeda Galaxy. It's the nearest large galaxy to the Milky Way. It's about the same size as the Milky Way. It's 2.5 million light years across. It's just about a naked eye object if you go to a very dark site and have a good eyesight. I must admit, I've never managed to see it with the naked eye, but through binoculars it's a really spectacular sight. It has two satellite galaxies. You can see one here and one here, and these correspond to this Large Magellanic Cloud, the subgalaxy, one of the two subgalaxies. The other one is imaginatively called the Small Magellanic Cloud, which orbit our galaxy. These two subgalaxies correspond to those. They're in orbit about the Andromeda Galaxy. Well, as you probably know, the universe is in general expanding, so we see all distant galaxies as receding from us. But close galaxies, the local motions within our particular cluster of galaxies can be more significant than the overall expansion of the universe, which is more important at larger distances. And actually this Andromeda Galaxy is on a collision course with the Milky Way. And in about 3 billion years, the two galaxies will collide. So you can worry about that if you like. So we're now 11 million light years away. This is another galaxy. It's called the Cigar Galaxy because of its shape. It's classified as an irregular galaxy. Galaxies tend to fall into three main categories: spiral galaxies, like the Andromeda Galaxy we just saw, and Milky Way is another spiral galaxy. Spherical galaxies, which are just like big balls, and irregular galaxies, which have no particular structure. Now, the rather chaotic appearance of this galaxy is probably due to the fact that it's relatively close to a large spiral galaxy, which you can't see on this image. It's outside the field of view. This large spiral galaxy called M81 has probably disrupted the structure of this smaller galaxy with its tidal gravitational force, starting about quite recently, about 500 million years ago. And what's happened is that it's pulled a lot of the gas in this Cigar Galaxy out of the equatorial plane of the galaxy, and these pink filaments that you can see to the top and the bottom, they look quite small, but actually each one is thousands of light years long and contains millions of solar masses of material. And although it looks as though it's kind of exploding, these filaments are actually falling back into the plane of the galaxy. So after its near passage by the large spiral galaxy M81, which pulled a lot of this gas out of the galaxy, now it's got a bit further away. The gravity of the Cigar Galaxy is pulling all this gas back into the main body of the galaxy, and because of all this disturbance, a lot of it is glowing with this pinkish emission light. So now we go a bit further away. This is my favourite galaxy. I've even got a T-shirt with a picture of this galaxy on it. It's 21 million light years away, and it is massive. It is larger than the Milky Way. It's 170,000 light years across and has about twice the mass of the Milky Way. And it's because we're looking at it from the perpendicular direction, we can see clearly the spiral structure with the many spiral arms of this galaxy swirling around the central core. And also you can see here, for example, and here, the typical bright bluish light of star-forming regions. It's a wonderful sight, and in fact, just a couple of months ago, there was a spectacular supernova in this galaxy. Slightly further away, the Whirlpool galaxy, and this is interesting because it's interacting with this smaller galaxy. Here you can see this tidal effect I mentioned. It's the same principle by which the moon causes the tides on the Earth. The smaller galaxy, the side of the smaller galaxy nearer to the larger spiral is attracted more strongly by the spiral's galaxy than the part which is further away. So this actually has the effect of trying to pull the smaller galaxy apart. And you can see there's a tail of matter streaming off here. The astronomers call this a tidal tail. And this is typical when a galaxy is disrupted by gravitational effects. But the larger galaxy has also been affected by the gravity of the smaller galaxy, and it has provoked a very dynamic star formation virtually throughout the larger galaxy, which is why the spiral arms appear particularly clear and distinct in this galaxy. A little bit further away, now this galaxy is interesting. Well, first of all, it's got a little satellite galaxy down here, but this galaxy is interesting because it has an unusual nucleus which is emitting particularly large quantities of radiation. And astronomers believe that's because there's a black hole in the center of this galaxy weighing about 30 million times the mass of the Sun. Now, our own galaxy has a black hole in its center, believed to be about 4 million solar masses, but this one is much larger. However, it's not the largest on record. Some distant galaxies have been measured as having black holes in their center of up to 1 billion solar masses. But this is a relatively nearby galaxy that has a very substantial black hole in its center.
Can a galaxy have more than one black hole?
Well, it's possible. I mean, black holes tend to come in two different sizes. Most galaxies, or we believe most galaxies, or these sizable ones, have a black hole, a central black hole at its core. And black holes of smaller size can be made by the collapse of giant stars. Now, so there may be a lot of these smaller stars sprinkled around a galaxy, but in generally speaking, there's always a central one. And it's one of the problems of cosmology at the moment that nobody really knows whether the galaxy forms and then the central region collapses to form a black hole, or whether the black hole forms first and the gravity of the black hole attracts lots of matter to form the galaxy around it. It's a kind of chicken and egg argument, and this question is still being debated. Now we go a little bit further. Now it's always nice when two galaxies are in the same field of view. Now it looks likely that these two galaxies are very close to each other, but in fact one is somewhat more distant than the other. The one on the left is about 35 million light years away, the one on the right about 40 million light years away. So, okay, they're sort of relatively close, but 5 million light years is really a big distance, believe me. This galaxy on the right, M66, again shows this, the kind of blue colour and these dark lanes, the prominent spiral structure, which is indicative of a burst of star formation, possibly caused by the gravitational effect of another galaxy, which is not visible in this image. So, you know, in a galaxy, the distance between stars is really enormous compared to the size of the stars, but that's not really true with galaxies. You know, the distance between galaxies is large, but it's not absolutely colossal compared to the size of the galaxies themselves. So, for example, from us to Andromeda is only 20 galactic diameters. And so here you can see that the size of the galaxies isn't so small compared to the distance between them. So, well, two stars are like us and the nearby star. It's like a cork in the Arctic Ocean and a cork in the Antarctic Ocean. But with galaxies, it's just like two coins held like this. You know, they are much closer together than stars within a galaxy. So now we're reaching the end of my little trip. We're now 60 million light years away, although our journey isn't over, because I think Christian is going to show you later something that's a lot more distant than this. But this is as far as I've gone with my astronomical photography. 60 million light years, and typical spiral structure, and also again satellite galaxy, similar to the Magellanic Cloud that orbits our own galaxy. All these other stars, as always in these images of other galaxies, these stars are stars within our own galaxy that happen to lie within the same direction. So that really wraps up my little tour, going further and further into the distance, and only really scratching the surface of the universe, because astronomers with their large telescopes and with the Hubble Space Telescope have peered back about 13 billion years into the past to see objects that were formed when the universe was only 10% of its present age. So while these pictures are like miracles of technology, because the amateur telescopes you have today, because of advances in technology and particularly in the detectors used, mean that these small, relatively small telescopes can produce images which are as good or better than the giant, best telescopes in the world, these giant telescopes of 60 or 70 years ago. So this is really a wonderful era for both amateur and professional astronomers, with new telescopes and new tools and space telescopes providing the information and the data for gigantic advances in astronomy and cosmology. Okay, well, thank you. I've finished mine. I'd just like to thank my son for the title sequence. Christian.
Okay, what I'd like to do now is just give you a little bit of background how it's actually possible to take such beautiful images as John has shown. There are basically two types of telescopes. The one is built from lenses and the other one's from mirrors. Okay? A lens is similar to what your binoculars look like. It's an optical system that produces a certain magnification. And if you want to really go to larger resolution, you actually go to mirrors. The main reason for that is that technology has advanced a lot in recent years, and the structural stability that you now have with fiberglass that gives you the mechanical stability, as well as the mirror surfaces that can be polished, are very lightweight and very large, and the resolution has become fantastic. That shows you a typical telescope. What surprises many people is actually the mount. You can see it's a fairly small telescope. It's actually a refractor. But what you can see, what many people underestimate, is the mount. Because if you do any imaging at high magnification, and especially these telescopes are remotely controlled, that's actually how John got his images. He remotely logs in, and you can log in from anywhere, even from the airplane if they have internet. You can take images, but you are leading basically a highly technological system which is blind and has to go to any point in the sky with very high precision. And that explains why you need such an incredibly stable mount, and the mount actually consists of a high cost of the total telescope. It's quite complex, actually. That's a more modern telescope. It's probably one of the best makes I know now. I actually went to the company in California called Planewave. And that's quite a young, dynamic team that has worked out a new type of technology. It's come up in recent years, and it's based on mirrors, certain shapes of mirrors. And you can see the technology looks fairly simple, and it's very, very attractive because light comes in, there's a primary mirror, reflects it onto a secondary mirror, gives you some magnification, goes through the center onto the detector. It's very well balanced from a mechanical point of view, and it doesn't really get much better than this. Fortunately, the advancement in digital technology, especially with our camera, becoming such a commodity has given an enormous boost to technology for astronomers. We're all lucky because the prices have dropped tremendously. If you look at what happened between 2000 and now 2011, it's just fantastic. This is what a typical digital camera for a telescope looks like. It looks most unfamiliar to you because mainly because it has such a huge body. I'll explain to you why that is the case. And then you see a second thing. There's a filter wheel here. Now, there are really two types of cameras. The one type of camera is a color camera, very similar to what you have in your digital camera. But what is much more attractive, and that explains the beautiful images that John was taking, is when you separate wavelengths into red, green, and blue color, and you superimpose these to get a color image of your choice. So what John was really showing you is not really the true color. You can see in galaxies and nebulas whatever you choose to see, and it usually is not what you would see with the eye. This shows you a bit of the sensitivity of these modern cameras. What you see here is the detection efficiency. That gives you, that's a measure for how many quantum, how much light is actually turned into a usable signal. And what is interesting here, that's the wavelength of the light. All you have to remember is that the human eye typically has a sensitivity between about 450 nanometers to 650 nanometers. You can see that's the visible light spectrum is only a very small proportion of what is interesting. If you look at the typical CCD camera, what it can cover, it's much more sensitive and covers a lot more on the red side of the spectrum. And that's actually where a lot of the hot gases become very interesting, and you'll see why. Now, there's something about these CCD cameras in the form image. It has a rather large body, and the reason for that is we cool the chips. Now, why would you do such a thing? John was mentioning that typical exposure time, sometimes you have an hour of accumulated or stacked images, which are typically 5 minutes long. If you use your digital camera and you do a 5-minute exposure, you're going to get a lot of so-called thermal noise in there. Thermal noise will cause you a lot of problems with your image because it'll distort what you're trying to see. So what one does is one gets rid of the thermal noise as much as possible by simply cooling the chip. Typical cooling temperatures are around minus 20 Celsius, and for extremely sensitive cameras, we go to minus 45 Celsius. Oops, sorry. Now how do I get back, John?
I'll get back.
Yeah. And this is what John was actually doing with a color filter. In order to produce a color image, he was taking a red, a green, and a blue image, and also what we would call a white image, which covers the whole spectrum. And by superimposing these, he gets a color image. And he would typically do this with special software. And finally, he would use Photoshop to stretch the image, and you get a beautiful image such as this. Now, this is what a typical agglomeration of telescopes looks like. You can see it's quite crowded, it's high-tech, and it's very difficult to control so many telescopes in one space. This is, by the way, the site in New Mexico. That's a more romantic view of astronomy. That's how we all like it. That's a site in Spain. Now, to your disappointment, we don't use these type of domes because very often the technology doesn't work the way you want it. As you can see, there's a small window, and sometimes the dome window is not looking in the same direction as your telescope, and you wonder why you see darkness. So what we use instead is a very simple roof that can just be pushed back, and that is much more reliable. Actually, you want as little technological hazards as possible. That's a typical control room. That's looking beneath the software that runs the whole thing. Vichy is going to show you, demonstrate this to you. And on the lower surface of the software, it's quite complex. There's software that controls the camera, software that controls the telescope, etc., etc. Now, it's quite interesting because John was already mentioning that if you take images in London, you won't see very much. But this is actually a person called Norman Faller, and he lives on the outskirts of London, and he's done most incredible asteroid hunting with remote telescopes. So it shows you what is actually possible. So you can sit anywhere, basically. It doesn't matter whether you have light pollution. You have the advantage you can take the most incredible images. Another possibility is comet hunting, which is quite exciting. I think Vichy will show you a beautiful image later. And this is rather interesting because John was referring to hypernovas, which is the superlative of a supernova. And that's very interesting because we now have satellites up there that are very, very sensitive and can detect so-called gamma bursts from massive stars that explode. And within a few seconds, you see a massive gamma burst, and then comes what you call an afterglow. And the afterglow can last from several minutes to several hours. So this is a group of Finnish amateur astronomers who have actually used the system to detect such an afterglow. Now to something else that's exciting, was John was alluding to, an interesting question, how far can we actually go? And this was me in 2000, 2001, actually in South Africa. I looked a lot younger there, and that's how I started. That was a farm in the middle of nowhere, and that's how I got my interest in astronomy. You can see we had very simple equipment at that time. And I had a similar setup in Sweden, and I was taking the Sombrero Galaxy at that time. I was very proud of starting, and then the neighbor came to me and said, well, how far is that away? And I said, well, it's about 30 million years. And his next question, well, how far can you see? I thought, what a crazy question is that? And that question bothered me ever since. I actually became obsessed with that question because it's actually a very, very clever question. And I tried a lot with simple telescopes. I didn't get very far for several reasons. So a lot has happened between 2000 and 2010. In 2007, there was a group of very capable amateur astronomers, and they were looking out for quasars. Now, quasars are very well known to professional astronomers because quasars are the most luminous galaxies that you can find. And what's interesting about quasars is they are very, very far away. And very, very far away in astronomical terms means there's a very, very large redshift due to the expansion of the cosmos. So these amateurs were looking at a certain quasar, and they found it close to 12 billion light years away, and they actually managed to capture this. That was to my large annoyance because I wanted to be the person who was going to do that. So what was left to do is to go even further. So I looked a lot at this, the sensitivity of technology, and I had a lot of years of a lot of problems getting there, but finally composed a system that would actually be able to image the second furthest away quasar that is known by large telescopes. By large telescopes, I mean telescopes with a diameter of 10 meters. Now, to compete with these guys is extremely difficult because, I mean, look what you're seeing here. This is what you call the spectrum of a quasar. If you remember, the sensitivity of the eye is way, way in the visible. We're looking in what you call the far red. It's not the infrared, it's the far red. And you can see a quasar is opening its spectrum because there's such a enormous redshift due to the incredible distance of that galaxy that the hydrogen lines that you see from the emission are actually incredibly redshifted and very, very difficult to detect. So I looked at the system carefully, and I finally chose a sensor that would be able to detect this. Here you can see the high redshift quasar, and I chose a special type of sensor for that. And with the help of some other amateur astronomers, we actually built the system. And you can see the quantum efficiency where the quasar is fairly high, it's 70%, and then drops. A usual CCD camera is completely blind in that region, and there's no way you can detect it. So in February 2011, I succeeded to my big surprise and also disappointment, because once you get there, it's a big climax, and at the same time, how on earth did I get here? So this is this very distant quasar that appeared after 16 hours of stacking images. It suddenly appears, and it's not really spectacular as the images that John was showing. That's because it's 12.7 billion light years away. So what is interesting is you have a telescope like this, and you're detecting light that is 12.7 billion years ago. That is 850 million years after the universe was born. And for me, that was very, very exciting to have done that. Okay. what I'll do now is I'm going to hand over to Vichy to give you some practical demonstrations and to show a bit of the system. And we're logged into one of the systems here. Let me just see if I can.
Christian, do you want to switch computers now?
Yes, that's right, thanks. Let me just show quickly where the overview is. So this is what it looks like when you log into our system. You can see here a map of the Earth, and what you can see, there's some darkness and some light. So we have 3 sites. You can see there's one in New Mexico, and that's where it is daylight at the moment. Then the other one is in Australia, and you can see it's just shifted into daylight, so this curve actually moves west. And you can see this is full daylight, and here you can see the moon. And then there's a 3rd system in Spain, and that is in darkness at the moment. So that's the one we're going to use. So Vichy has done quite a few images, and he's going to give you a live demonstration now of a system in Spain. And at the moment, the moon is fairly high, so we have to choose a relatively luminous object. Let me just see which one this is. Right. Okay, I'll give it to you now.
Yeah. Okay, so I think you've seen how amazing this technology is. I mean, I got reinterested, if you like, in astronomy about 8 or 9 years ago. And so the first stage was using binoculars and simple telescopes, but the range of interesting things you can see with that runs out pretty fast. And I mean, first of all, the telescope itself starts to get heavier. I think John for some time was explaining to me how he practically needed to do weightlifting to get the stuff from his garden and back. And then there's the weather. And as you can see, I think Christian explained this very well, the mechanical and technical issues are considerable. So this actually is wonderful for someone who's interested in astronomy, wants to explore the night sky, but doesn't want to invest a hell of a lot of time doing everything themselves. And so I subscribe to a site which sends me an email every day with a list of interesting objects that I can use, and then I just sort of harvest that list and then see what I can find. So you take into account the time zones. Typically I do it in the morning because then it's night both in the States and in Australia. So it gives me more options. And there are a couple of other things you have to take into account. One is where the moon is, because the moon tends to be incredibly bright. And the biggest problem is clouds. There's very little even the best systems can do against that. But there is it's fairly straightforward. I think we've already seen the, okay, I just go. Well, you already saw the panel where you have your membership and you get to see what's in the sky. And you can also choose from a list of telescopes.
Go down there. One of those there.
Ah, that's right, yeah. You can choose from a list of telescopes. We are going to use G16 in Spain. And that depends again whether you want a wide field view or a narrower one. It's all pretty simple. Essentially, you log in, you get this page, you pick your telescope, and that's the one. Then here you get a nice chance to see what the sky looks like from the viewpoint of the telescope. So you can make out if there are a lot of clouds, then there's no need to waste time. You can come back later or just check if the weather is going to improve. Here we can see again that the moon is quite high in the sky. And then you get a list of suggestions, tonight's finest objects. We're going to do M31 today, that's Andromeda. And literally, you take your mouse, you go here and you click submit. You can also decide whether you want a one-click image, or a single image, and then you can take the LG, RB, luminance, green, red, blue. You can set the number of seconds for the exposure, etc. It's amazingly simple to use, and it takes out all the hard stuff and allows you to just enjoy the night sky. So shall I click submit?
Yes, go on.
Good.
Oh, no, he put it off.
Okay.
We'll take another.
Okay.
Take another one.
Which one should we do?
Let's see. Maybe they got some. Try G7. That's okay. I think it's already there somewhere. G7, I think it's here. No, that's
Yeah, cross that. Sure.
I take it from there.
One click, right?
Yeah.
Yeah, so we'll try Andromeda anyway. And then you can just go to system status over here and always see what's the current situation. I mean, if you're looking for a very complicated demonstration, it's essentially dragging your mouse and clicking a few things. I wish it was more fun, but that's it. So, and then I think John also has some of the photos I've taken.
Yes.
So maybe we can show that while we're waiting for the results. And it's that easy. And you don't have to only go for these objects. You can also select any target you want, depending on if it's possible. Another good thing, of course, here is you have the whole range of stars that are available from planet Earth. You're not restricted to stuff in the northern hemisphere or southern hemisphere. You get to choose really a huge list of objects. And if without traveling there, if you want to take something in the southern hemisphere, the system is fantastic. Okay, so shall we see system status? Yeah. Yeah. Well, you can see here, it gives you, the summary is fairly self-explanatory. It's turning, it's looking, it's taking, whatever. And that's it. So shall we show my photos while we're waiting?
Yeah.
So,
Yeah.
and you can see it's now starting to operate. I mean, it is, I think, a kind of miracle to be able to use this kind of hardware. And I mean, the mounts and everything, it's amazing to think that you can do this from anywhere. And nowadays, probably even from the phone. So it is a wonderful thing. Okay, we can.
Okay, we switch over. You just click to advance. But don't press the X, it's on already.
Yeah.
Okay, just there, it's on.
Okay, so these are some of the images I took. I don't think we covered the Eagle Nebula before. The Eagle is where the pillars of creation are, right?
Yeah.
That's a huge cloud, a nebula, like John explained, where stars are forming. And this one was a particularly amazing photograph, and it's called the Pillars of Creation, which is very famous. Okay. Eta Carinae. This is the largest star in the Milky Way. And here it's nice. We actually get to see a comet with a globular cluster in the background. So the cluster is over here, and you can see the comet Gerard move across it. That's M13. I think you touched on it as well. No, you didn't.
No, I didn't. No,
Okay. Yeah, the Dumbbell Nebula. This is one of these incredibly beautiful objects, so we all end up taking pictures of it.
Photoshop this one more than John.
Yes.
I should say that this is a very nice object if you have binoculars, because it's relatively large, and under a dark sky it's very easy to see with binoculars. It looks like a kind of faint cloud, but you have to know where to look, obviously. But there are many free software programs that you can download to navigate your way around the night sky. And if you have an iPhone or an Android, you can put something on this phone. And in fact, so with some of these, you can, with these phones that can detect your movement, you can hold it up, and it will show you what objects are visible in that direction. And if, like me, you hold it down, it will show you, as if the Earth was transparent, what you could see if you were in Australia.
So Andromeda, what we're taking again today, and the Pleiades. This is an incredibly beautiful object because in Spain I could see it with the naked eye. Of course, you don't see this level of clarity, but you see a small bunch of stars, and you can see there's something there, and it looks like there's a bunch of stars clustered. With binoculars, of course, the view improves tremendously, but this kind of view is obviously very nice to have. And yeah, so this is the whirlpool, and with that, yeah, with the supernova explosion. I think John also explained that what happens is when you have these huge gas clouds, nebula, these supernova, when this star explodes, the shock waves from this star can start the compression of neighboring clouds. So in effect, the death of this star will lead to the birth of many new solar systems and stars, which is why they're such fascinating objects to see. The other thing is, of course, that supernovae often shine as bright as their whole galaxy, the host galaxy. So that again is a very exciting object to get. But when you get one like this with the background, it's M101. I think there's even one where I took with Alina, but okay, I think that isn't here. Ah, okay, sure. And yeah, it went down. So, yeah.
Can I ask John a question just about why a lot of galaxies seem so bright? Can you hang on 1 second? I'll just go grab it.
Did we? Oh, this is 16. Okay. Yeah.
There's a question for John. I just wondered why lots of galaxies are.
Describe them as being thin.
Why they appear thin?
Yeah, so they're quite long and
yes, well, it
wide.
depends on the angle you see the galaxy. Remember, they're disks. So if the disk is, you're looking from, not in the plane of the disk, you see this spiral structure. But if the disk is tilted so that you look at it from the edge, then you see a long, narrow structure.
Why aren't they, say, spherical? I mean, if there was a Big Bang ages ago, why didn't it all go sort of spherically out?
Well, it did. It did, yes. I mean, the universe, we think, expanded more or less equally in all directions, although there are some slight differences which show that there is some large-scale structure, but that's only like maybe 1% difference between one area of the sky and another area of the sky. But when the galaxies are formed by, well, we think, by the collapse of very early in the universe of huge clouds of gas, and because of like conservation of angular momentum, when the gas cloud collapses, the rotation speeds up, and that automatically leads to this disk spiral structure. And later on, very often when two spiral galaxies collide, the result is one of these spherical galaxies. So there's some discussion as to what creates the spiral structure and this disk-like structure, but probably that is an earlier stage in the lifetime of a galaxy than the kind of spherical form you get later. Yeah.
How sure are you of your distances and why?
Distances, particularly on large scales, distances to other galaxies are difficult, and I've given like the average figure, but often there's an uncertainty which can be like 10% or even more in distances. The distances to nearby galaxies are known fairly accurately.
How do we know that?
Well, it's because there's a certain type of variable star called a Cepheid variable, and it's known that these variable stars, the period of their variation is related to their what's called the absolute luminosity, how actually bright they are. So by looking at the period of their light fluctuations, you can work out their absolute luminosity, and then by comparing that with the brightness you actually observe, you can calculate the distance. So for the nearby galaxies where you can see individual stars, you can say with more confidence what the distance is. But even in that case, there is a significant uncertainty. So we're talking about maybe a 10% uncertainty. I mean, it wasn't that long ago people were saying the Andromeda Galaxy was 2 million light years away. Now they say it's 2.5 million light years away. So there you've got some error. And when you go to these very distant galaxies, almost the only measure you have is their redshift that Christian was talking about, which basically tells you how fast they're receding from you. And now we just assume, although there's a lot of evidence for it, that the redshift is proportional to the distance they are away from us. But obviously here there's more guesswork involved. And so when I give a distance, particularly to these extragalactic objects, even for many objects in our own galaxy, the distances are not known with any great precision. And in some cases, you will find different research papers which give figures that differ by 10–15%, something like that. So yes, it's a good question. The distances are very difficult to calculate.
Vishay, how did you find the supernova? Did you read about it, hear about it, and then go and search for it?
Yeah, I mean, you can pick an interesting object. Like I said, you can either subscribe to it or anything you read, and then you can go and look in that area knowing that that supernova is in that image. And take.
Last the supernova?
Should be several weeks or...
So you had to catch it?
Yes, I mean, you can't put it off for a couple of years, I think. But supernova do lie in the sky for a couple of weeks. So.
And John, what lights up the Veil Nebula, if it's thousands of light years across?
Yeah, well, as I say, it's a kind of shock wave. So expanding material from the supernova crashes into the interstellar medium and heats it up.
So it's not being lit up by a star?
No, it's not. It's not like an emission nebula.
And the lighthouse star, I think, John, again, you mentioned a lighthouse star, which
yes.
Surely a star is light on all sides. How do you get the pulsating image that
with
you were
most
describing?
stars that's true, but for example with pulsars, with these dense neutron stars, they rotate very fast. They also have an incredibly strong magnetic field, and because of this, a lot of the material around the star, or material that's ejected, high energy particles, because the light we're talking about is emitted when high energy particles thrown out by the star collide into the surrounding material. And these high energy particles are funneled by the magnetic field into beams which rotate with the star. So yes, with most stars that's true, but with these very small dense stars, particularly ones with large magnetic fields, we're talking about really colossal magnetic fields here, which are like trillions of times stronger than the magnetic field on Earth. You get this kind of beam effect, this pulsating effect.
If you're going to I'm not a very great chess player myself, I just read papers and you ask. I was going to say if you compared Fisher to a collapsing star, then I suppose what you're doing, sort of Vishy, and you're like forming galaxies is a much more healthy way of playing.
Well, it's always nice to see these star-forming regions, because you have to think, well, okay, there's a lot to look forward to in the universe. It's not all dead stars and collapsed stars and so on.
More healthy to have a variety of interests as well as chess.
Well, I think it's, yes, I mean, chess players traditionally have had some problems with their mental stability, and I think some interests outside of chess probably do help to keep a foot in the sky, even if not on the ground.
Would you agree with that, Vishy?
Yeah, very much. But also, in this case, it's simply that technology suddenly made it much easier to follow a very difficult subject. I remember when you had to get these guidebooks and keep them and sort of keep shifting this a map of the sky, and now it's just so easy. You can just put your location, your coordinates. Even if you can't be bothered to find your coordinates, just put the name of the nearest city, and you can get a map of the sky generated for years before or after, and all that. So, and then plus the developments in digital technology and just everything has made something that would have probably, the complexity would have dissuaded me before, but now it's so much fun to do that. It's nice, and I think it does help relax if you can do something else other than chess. So.
Very informative. Thank you.
So here we get a relative comparison of the size in the sky. So the moon is here. That gives you a picture. Yeah, and that's the Andromeda galaxy as it would look if you could see it. And you can see the satellite galaxies there. Should we go back to the image?
Could I ask you a question? I mean, the microphone is 2 million light years away. Thanks a lot. It's just this mystery over time. You're both speaking affectionately about, say, nebulae and things you've seen in the present tense. You say is all the time, you know, this is, and we see this as it, although these things have happened a huge amount of time ago. So if, for example, what you showed us 24 million light years away had completely destroyed itself 12 million light years later, it would all be gone 12 million light years ago. Is that not correct? It wouldn't exist. Though we're seeing the messages, the molecules send 24 million light years, which we pick up now.
Yes, you're correct. When you look into the distant sky, you're looking into the past because you're seeing the light that was emitted millions of years ago. But of course, when you look at a distant galaxy, these are galaxies that have been around for billions of years. So, you know, a few million years here or there isn't actually going to make a huge amount of difference.
Yes. But I mean, some of what you're speaking about may no longer exist at all. I mean, maybe in bits somewhere else, if you see what I mean.
Yes, I mean, it's true, for example, these planetary nebulae that I was talking about often only last for a few thousand years. So if you look at one that's 10,000 light years away, it won't be there anymore. But otherwise, the use of language is a little bit complicated. We tend to speak in terms of when we see it, the first moment that we can see it, and we say, well, okay, that's now, whilst keeping in the back of our minds that actually that was thousands of years ago.
Yes, but it leads a lot of people to speak about crazy things like aliens arriving and how they were in the back garden and kidnapped them and took them away. About 150 years ago, no one described aliens or anything until the electricity happened and until light was bouncing out of clouds. Nobody spoke about the possibility of anything to do with aliens.
I mean, if you want to ask about aliens, I think you should speak to the FIDE president.
But that is the point, talking about nebulae as if they exist now seems, could have the effect of making people think it's all now a now event. Therefore, there are aliens, etc., etc.
Well, I think this is, again, with geological timescales and astronomical timescales, the usage of tense becomes very... I mean, there's this funny story of a janitor who works in the museum, and there's an exhibit which was 3 million years old. And so somebody asks him, well, how old is, when was this dinosaur around? 3 million and 3 years ago. And says, how do you know